In a previous video, I talked about a copper wire that was the diameter of a penny. I said that this penny contained 130,000 coulombs of electron charge. And we gave the example of 1 amp of current flowing in this wire. And since 1 amp is a coulomb per second, let's solve a problem. How long would it take for the charge in this penny, 130,000 coulombs of charge, to pass the surface of this penny with a 1 amp of current flow, which is a coulomb per second? So put the video on pause and see if you can solve that problem. Okay, so I'm assuming you solved the problem, and let's see how that was done. If we have 130,000 coulombs that must pass the surface of the penny, and we're only moving a coulomb each second, it's going to take 130,000 seconds for the charge in the penny to pass the surface of the penny. Now let's convert that to minutes. We know that 1 minute is equal to 60 seconds. And so our seconds will cancel out and we'll be left with minutes. But let's convert that to hours. Times, we know 1 hour is equal to 60 minutes. So again, our minutes will cancel here and we'll be left with hours. And when we divide by 60 twice, we'll get 36.1 hours. So the electrons are moving very slowly in this copper. So they're moving along and they're encountering obstacles. If, for example, they'll encounter the positive nucleus of the copper atom, and the electron will, maybe it'll bounce back for a while, and then it'll continue on with its flow, and it'll hit another nucleus or it'll hit an electron. But it's not a rapid flow of current. Now, why when I turn on a light bulb, I flip the switch, that light bulb turns on almost instantly? If the electrons are moving so slowly, why does that bulb turn on so quickly? Well, let's consider that. Let's do an analogy. Let's say we have a cross-section of a garden hose. And inside of this garden hose we have a bunch of marbles. Now, if I push on the marble at the left side, the marble at the right side is going to pop out almost immediately. Although the motion of the marbles within the hose are rather slow, this impulse, when I cause an action on the left side, I get a reaction on the right side that happens almost instantly. And it's like that in the copper wire. When I apply an electric field in the wire, these electrons all move together, but they're all moving continuously within the wire, and that makes that light bulb turn on very quickly. In fact, this impulse is traveling at almost the speed of light. It's extremely fast. Let's solve another current problem. Let's say we have a copper wire with a branch. In electronics, we call this branch a circuit node. Let's say that we put an ammeter in this branch. We'll call this A for ammeter. An ammeter is just a device that measures current flow. Let's say we put another ammeter in this branch. Let's say that the ammeter on the left measures a current flow towards the right of 1 amp. Let's say the ammeter at the right measures a current downward at 1/2 amp. The problem is, what is the current in the other branch? What is the current flowing to the right out of this branch? It stands to reason if we have a current of 1 amp flowing into this node and a 1/2 amp flowing down out of this node, that we must have a 1/2 amp flowing to the right. We don't have to put an ammeter in the branch at the right. We know that this is true from conservation of charge. So to summarize, there's a rule about the current flowing at a node. And the current flowing into the node is equal to the current flowing out of the node. In this case, flowing to the right, we have 1 amp, and flowing down a 1/2 amp, and flowing in this other branch a 1/2 amp. So everything sums to 0. So what goes into the node comes out of the node from conservation of charge. And this is called Kirchhoff's current law. Kirchhoff's current law.